Right now, the concentration of carbon dioxide in our atmosphere is higher than at any point in at least 3 million years. Not higher than during your grandparents' lifetime. Not higher than during the Industrial Revolution. Higher than at any point since a time before our own species existed in anything like its current form. That is not a dramatic exaggeration designed to scare you into watching a video. It is simply where the instruments say we are. And it is worth sitting with for a moment before we go any further. In the middle of 2025, a widely respected environmental scientist said, in plain terms, that humanity has lost the fight against climate change. That single sentence spread quickly because it is the kind of statement that either makes you angry, makes you numb, or makes you want to look away entirely. This is not going to be a video that tries to comfort you out of that reaction. Instead, it is going to walk through the actual data, the actual history of what governments promised and what they delivered, and the actual science of where the planet stands today, so that you can decide for yourself whether that statement holds up. Before we get into the numbers, it helps to understand what we are even measuring when we talk about climate change, because the phrase gets thrown around so often that its precise meaning tends to blur. Earth's climate is, at its core, an energy balance problem. Sunlight arrives, some of it bounces back to space, and the rest is absorbed and eventually radiated back out as heat. Gases like carbon dioxide, methane, and water vapor sit in the atmosphere and slow down that outgoing heat, trapping a portion of it near the surface. This is not a modern discovery. Scientists were describing this basic mechanism, known as the greenhouse effect, as far back as the 1800s, and by the 1950s, researchers had already begun measuring rising carbon dioxide levels directly from the air itself. What has changed since then is not the physics, which has remained rock solid under a century and a half of scrutiny, but the scale of the experiment we are running. Since the start of large-scale fossil fuel burning around the middle of the 1700s, humanity has added enough carbon dioxide to the atmosphere to raise its concentration by more than 50% above the level it sat at, for hundreds of thousands of years before industrialization. To put that in perspective, ice cores drilled from Antarctica let scientists reconstruct atmospheric carbon dioxide levels going back roughly 800,000 years, through multiple ice ages and warm periods. Across all of that time, the concentration never exceeded roughly 300 parts per million. Today, we sit above 425 parts per million, a level this planet has not experienced in millions of years, reached in the span of a couple of centuries rather than tens of thousands of years. On a geological timescale, that increase looks less like a gentle slope and more like a vertical cliff. So how did the world respond once scientists sounded the alarm? To understand where we are now, it helps to look at what was actually promised, meeting by meeting, decade by decade, because the story of climate policy is really a story of steadily rising ambition paired with steadily rising emissions, running in parallel, almost as if they had nothing to do with each other. For most of the 1970s and 1980s, climate change was a subject for scientific journals, not international diplomacy. That began to shift in 1988, when the United Nations helped establish a body dedicated purely to synthesizing climate science for policymakers. Its job was never to lobby or campaign, simply to gather what researchers around the world had found and present a clear picture, so that governments could not claim ignorance. 4 years later, in 1992, representatives from most of the world's nations signed a framework treaty agreeing, in careful diplomatic language, to prevent dangerous human interference with the climate system. It sounded promising. It committed nobody to a specific number, a specific date, or a specific consequence for failure, but it set the stage for everything that followed. The years immediately after that agreement happened to bring a small, temporary dip in global temperatures, not because of any policy success, but because a large volcanic eruption threw enough sulfate particles into the atmosphere to briefly reflect additional sunlight away from the surface. It was a reminder that the planet's climate can be nudged by natural forces as well as human ones, but it also gave false comfort to anyone hoping the problem might resolve itself. 5 years after the initial Framework Treaty, in 1997, a more specific agreement was reached in the city of Kyoto, Japan. This one asked a group of 37 industrialized nations to cut their combined greenhouse gas emissions by an average of 5% below 1990 levels, over a commitment period running from 2008 to 2012. Reasonable people can debate whether 5% was ever going to be enough, but the more revealing detail is procedural. Because of the ratification process required for the agreement to take legal effect, it did not actually enter into force until 2005, 8 years after it was signed. By the time the treaty had legal teeth, a third of its already modest commitment period had already passed. 13 years after that initial framework treaty, in 2010, a further round of talks in Cancun, Mexico produced what was, at the time, a genuinely significant shift. For the first time, negotiators attached an actual temperature number to the conversation, agreeing that the rise in global average temperature should be limited to below 2 degrees Celsius above pre-industrial levels. This was the first time the abstract goal of preventing dangerous interference with the climate system had been translated into something measurable. Almost immediately, though, further research complicated the picture. Studies on vulnerable ecosystems and low-lying nations found that serious, sometimes irreversible damage could occur well before that 2-degree mark was reached, which meant the newly agreed target might already be too loose to protect the places most at risk. 5 years further on, in December of 2015, nearly every nation on Earth, 195 in total, gathered in Paris for what remains the most significant climate agreement in history. The resulting accord asked the world to keep global warming well below 2 degrees Celsius above pre-industrial levels, while making active efforts to hold that rise closer to 1.5 degrees, recognized as the safer threshold for the most vulnerable regions and ecosystems. This was the moment the argument that humanity simply did not understand the scale of the problem stopped holding up. By 2015, the science, the risks, and the stakes were about as clear as they were ever going to get. What happened next is where the story turns from a history lesson into the reason for the discomfort building. Throughout this video, that 1.5 degree figure deserves its own explanation, because on its own, 1.5 degrees sounds almost trivial. It helps to understand what the number actually represents. It is not a local temperature, like the difference between a slightly warm day and a slightly cool one. It is a shift in the average temperature of the entire planet's surface, calculated across oceans, continents, poles, and everywhere in between, sustained over long periods of time. Shifting that kind of planetary average by 1.5 degrees requires an enormous amount of additional energy trapped in the system, and small shifts in a global average tend to translate into much larger, more volatile shifts in extreme events at the regional level, which is really where the damage gets done. The other tricky part of that number is the baseline it is measured against. Scientists generally define pre-industrial levels using surface temperature records from somewhere between 1850 and 1900, even though most historians place the actual industrial revolution a century earlier, in the mid-1700s. This is not because climate scientists are careless with history. It is because reliable, widespread thermometer records simply do not exist much before 1850. Researchers are not trying to hide an inconvenient starting point. They are working with the earliest data that lets them separate human-caused warming from the planet's natural year-to-year wobble. Once the Paris Agreement gave the world a specific number to aim for, scientific institutions moved quickly to figure out what achieving it would actually require. In 2018, a special report was released warning that global warming was likely to reach 1.5 degrees somewhere between 2030 and 2050. 2. If emissions kept climbing at their existing pace. At the time, this still qualified as a warning about the future. There was still a runway. A few years later, a much larger assessment, released across several parts between 2021 and 2023, sharpened the numbers considerably. To have a reasonable chance of holding warming to 1.5 degrees, global carbon dioxide emissions needed to peak no later than 2025, then fall by around 43% by 2030, relative to 2019 levels, with methane emissions dropping by roughly 1/3 over the same window. So here is the uncomfortable part. It is now well past the point where those warnings were issued, which means we can check the receipts. And the receipts are not good. In 2025, the average concentration of carbon dioxide in the atmosphere reached a new record high, somewhere above 427 parts per million for the year as a whole, with the seasonal peak that spring pushing past 430 parts per million for the first time on record. For context, the last time the atmosphere held this much carbon dioxide, global temperatures ran several degrees warmer than pre-industrial levels, and sea levels stood tens of meters higher than they do today, because enough ice sheet had melted to fundamentally redraw the coastlines of every continent. We are not there yet in terms of temperature, because the climate system has a built-in lag between a rise in atmospheric carbon dioxide and the full temperature response it eventually produces. Some of the warming caused by today's emissions has not even arrived yet. It is, in effect, already banked for the coming decades, regardless of what happens next, and the growth shows no sign of leveling off. Between the annual measurements taken in 2024 and 2025, the concentration climbed by roughly 2 parts per million, continuing a trend where recent single-year increases have been among the largest ever recorded, faster even than the jump most years earlier in the record. Monitoring agencies have been explicit that there is no indication yet that emissions growth has peaked, despite that being the very first milestone required under the 2021 Assessments Roadmap. There is a second number worth understanding here, called the carbon budget, which is essentially an estimate of how much additional carbon dioxide humanity can release, while still having a reasonable chance of keeping warming under 1.5 degrees. At the start of 2020, that remaining budget was estimated at around 500 billion tons. By the start of 2025, updated research placed the remaining budget at closer to 130 billion tons, an enormous reduction in just 5 years. Global emissions currently run at somewhere around 40 billion tons of carbon dioxide per year, which means, on the current trajectory, that remaining budget could be exhausted within roughly the next 3 to 4 years, not the next 3 to 4 decades. Emissions are really only half of the story, though. The other half is what all that extra trapped energy is actually doing to the planet's surface. And here, the picture is just as stark. Multiple independent agencies, tracking temperature through thousands of weather stations, ocean buoys, and satellites, agree that the 10 years running from 2015 through 2024 rank as the warmest decade since reliable global record-keeping began in the 1800s. Not the warmest decade in recent memory, the warmest decade on record, full stop. And it happens to be the one we most recently lived through. Individual years tell an even sharper story. 2023 set a new record at the time. coming in at roughly 1.18 degrees above the 20th century average, translating to somewhere around 1.3 degrees above the pre-industrial baseline. That record barely survived 12 months. 2024 broke it decisively, reaching about 1.55 degrees above pre-industrial levels, meaning a full calendar year briefly crossed the exact threshold the Paris Agreement was built around. 2025 settled in as the third warmest year on record, trailing only the 2 years immediately before it, which is either a small mercy or simply evidence that the last 3 years occupy the top 3 spots in a temperature record. Stretching back over a century, it is worth being precise here, because nuance matters and the picture is not quite as simple as one clean line crossing a threshold and staying there. Natural climate patterns, particularly a warming ocean pattern known as El Niño, can push global average temperatures up temporarily on top of the underlying human-caused trend, then ease back down again. Scientists have been clear that a single year, briefly exceeding 1.5 degrees, is not the same as breaching the Paris target permanently, since that target is generally understood as a sustained, multi-decade average rather than one warm 12-month stretch. But even accounting for that natural variability, human-caused warming remains by far the dominant driver behind those record temperatures. And the overall trajectory of the baseline itself, El Niño years and La Niña years alike, keeps climbing. These are not abstract numbers sitting in a database somewhere. They translate directly into the kind of extreme weather that has increasingly become a fixture of the news cycle rather than an occasional shock. Late in October of 2025, a hurricane named Melissa underwent one of the fastest intensification periods ever observed in the Atlantic, strengthening from a tropical storm into a catastrophic Category 5 hurricane in under 2 days. It made landfall in Jamaica with sustained winds in the range of 185 miles per hour, making it the strongest hurricane ever recorded to strike that island directly, and one of the most intense hurricanes ever measured anywhere in the Atlantic basin. Rivaling storms that occurred nearly half a century earlier, sea surface temperatures in the region sat well above the historical average at the time, and researchers with the science non-profit Climate Central estimated the conditions capable of producing a storm this intense had been made hundreds of times more likely because of human-caused warming. Dozens of people across Jamaica, Haiti, and the Dominican Republic lost their lives, and damage across the region ran into the billions of dollars. Heat itself, without any storm attached to it, has become one of the deadliest consequences of a warming climate, precisely because it rarely makes for dramatic footage the way a hurricane does. A once-in-10-year extreme heat event, the kind that used to be a rare outlier in the pre-industrial climate, is now roughly twice as likely to occur at just 1.5 degrees of warming, and research has estimated that around 14% of the world's population would face severe, recurring heat waves once that threshold is reached. A major analysis published in the medical journal The Lancet projected that heat-related deaths would rise significantly compared to the 1990s. And more recent tallies suggest that heat-related mortality now sits well above 500,000 people every year globally. Even wildfire smoke alone, a secondary consequence of hotter, drier conditions feeding larger and more frequent fires, was linked to roughly 154,000 deaths in 2024 when researchers accounted for the fine particulate pollution it produces across entire continents downwind of the fires themselves. None of this is limited to any one region. Canada and Australia have both experienced wildfire seasons in recent years that burned through areas far exceeding historical norms, sending smoke plumes thousands of miles and, in Canada's case, blanketing cities across an entire neighboring country in an orange haze for days at a time. Extreme flooding has repeatedly devastated Pakistan, at times displacing tens of millions of people and submerging a scale of farmland that takes years to recover. Heat waves across South Asia and the Mediterranean have pushed past previous records with a regularity that meteorologists increasingly describe not as anomalies, but as the expected new normal. The United States alone recorded a record number of separate billion-dollar weather disasters in a single recent year, encompassing wildfires, severe storms, and hurricanes, a tally that has been climbing steadily for decades. Temperature and emissions are the numbers most people are familiar with, but there is a broader scientific framework that puts them in a much more unsettling context. And it is the framework that the environmental scientist referenced at the start of this video was actually pointing to when he made his warning. In the mid-2000s, a group of Earth system scientists, led by researcher Johan Rockström, identified what became known as the planetary boundaries, 9 distinct systems that, together, keep the planet in the kind of stable state that allowed human civilization to develop in the first place. These 9 systems include climate change itself, the integrity of the biosphere, changes to land systems through deforestation and urbanization, freshwater use, the cycling of nutrients like nitrogen and phosphorus through the environment, ocean acidification, the health of the stratospheric ozone layer, the concentration of aerosols in the atmosphere, and the introduction of novel entities such as synthetic chemicals and plastics that the natural world has never encountered before. The logic behind the framework is fairly intuitive once you hear it explained. Each of these 9 systems has operated within a relatively stable range for roughly the last 11,700 years, a geological period known as the Holocene, which happens to be the only period of Earth's history we know for certain, is capable of supporting human societies structured the way ours currently are. Push any one of these systems far enough past its historical range, and you risk triggering changes that are abrupt, self-reinforcing, or effectively permanent on any timescale that matters to a human lifetime. Think of the 9 boundaries less like a wish list and more like the safety margins on a piece of life support equipment. Staying within them does not guarantee comfort, but crossing them multiplies the odds of something going seriously, unpredictably wrong. As of the most recent comprehensive assessment, 7 of those 9 boundaries have now been crossed. Climate change, biosphere integrity, land system change, freshwater use, the nitrogen and phosphorus cycles, and novel entities were already assessed as breached in earlier reviews. The 7th, ocean acidification, was confirmed as crossed for the first time in a report released in September of 2025. Driven largely by the same fossil fuel emissions responsible for atmospheric warming, since much of the carbon dioxide humanity releases does not stay in the air at all. It dissolves directly into seawater. Since the start of the industrial era, that process has already lowered the average pH of the ocean's surface by around 0.1 units, which sounds small until you understand that the pH scale is logarithmic, meaning that seemingly tiny shift represents somewhere between a 30 and 40% increase in the ocean's overall acidity. Practical consequence of that shift falls hardest on organisms that build shells or skeletons out of calcium carbonate, including corals, certain plankton species, and shellfish, warm water coral reefs, which support close to 1 billion people through fishing, tourism, and coastal protection, and which host roughly a quarter of all known marine species, despite covering a tiny fraction of the ocean floor, have already crossed thresholds associated with long-term stability in multiple regions. Large-scale coral die-off events are already underway in several parts of the world, and without a reversal in warming trends, Reef systems, in something resembling their current form, are unlikely to persist through the rest of this century. Only 2 of the 9 planetary boundaries remain within what scientists classify as the safe zone, those being stratospheric ozone and atmospheric aerosol loading. And the ozone story in particular is worth pausing on, because it is one of the very few unambiguous success stories in this entire narrative. Back in the 1980s, researchers discovered that a group of widely used industrial chemicals, chlorofluoric, were steadily eating away at the ozone layer that shields the surface from harmful ultraviolet radiation. Rather than decades of stalled negotiation, the world moved with unusual speed, agreeing in 1987 to phase these chemicals out almost entirely. That agreement worked. The ozone layer has been recovering ever since, and current projections suggest it could return to something close to its pre-1980 state within the coming decades. It stands as clear proof that rapid, coordinated global action on an environmental threat is not some theoretical impossibility. It has happened before, on a genuinely global scale, within a single human generation, which raises an obvious question. If the ozone layer proves that coordinated global action works, why has the response to a much larger threat been so much weaker? Part of the answer becomes clearer when you look at who is actually responsible for the emissions driving all of this, and where the blame tends to get directed instead. A widely cited analysis published by the Climate Accountability Institute found that just 20 state-owned and private companies have been responsible for roughly 1/3 of all global greenhouse gas emissions released since 1965. Nearly all of them are fossil fuel producers, and many of them continue posting some of the largest profits of any companies on the planet to this day. Meanwhile, national governments collectively spent an estimated $956 billion subsidizing fossil fuels in 2023 alone, a figure that raises an uncomfortable question on its own. If these industries are as profitable as their earnings reports suggest, why do they continue receiving public subsidies in the first place, rather than shouldering the full cost of the product they sell at the same time? The framing of climate responsibility in public discourse has leaned heavily toward individual behavior: recycling more, driving less, eating less meat, lowering the thermostat by a degree. Some of this framing has surprisingly traceable origins. The concept of a personal carbon footprint, now a completely mainstream idea, was popularized in significant part through marketing campaigns run by a major oil company in the early 2000s, as part of a broader effort to shift public conversation toward individual consumer choices rather than corporate extraction and production decisions. It is worth noting that residential electricity use accounts for a relatively modest share of total global electricity consumption, commonly estimated at under 30%, with the remainder going toward industry, commerce, and transportation. In the third quarter of 2025 alone, one major oil company reported a quarterly profit exceeding $2 billion, a figure that dwarfs the plausible savings from any number of individual households turning down their thermostats. None of this means individual action is pointless, and it would be a mistake to walk away from this video concluding that nothing you personally do matters. The actual mechanism by which individual choices matter is simply more indirect than the marketing suggests. A single household reducing its energy use does not meaningfully bend a global emissions curve on its own. What does matter is the aggregate effect of visible behavior change across millions of people simultaneously, because that kind of shift builds a broader culture of climate awareness and, more importantly, sends a measurable political signal. When enough consumers and voters visibly demand change, it becomes harder for politicians and corporations to justify inaction, and easier for stronger policy to gain traction. The point of reducing your own footprint is less about the tons of carbon dioxide you personally prevent, and more about the pressure that collective, visible action puts on the institutions actually capable of shifting the emissions of an entire economy. It is also worth stepping back to the diplomatic side of this story once more, because the pattern of promise followed by shortfall did not stop with the Paris Agreement in 2015. Every year since, representatives from nearly 200 countries have gathered for what are called Conference of the Parties meetings, commonly abbreviated as COP, to review progress and negotiate further commitments. These meetings receive enormous media attention, complete with dramatic overnight negotiating sessions and last-minute compromises. And yet the substantive outcomes have repeatedly fallen short of what the science says is required. The most recent of these meetings, held in Brazil, once again ended without securing a clear, binding commitment to phase down fossil fuel production. Despite fossil fuels remaining the single largest driver of the emissions, the entire conference exists to address this disconnect between diplomatic activity and physical outcomes becomes even starker when you look at what governments have actually approved on the ground. While these negotiations were taking place, in the 12 months leading into 2025, governments around the world granted approximately 492 new oil and gas exploration licenses. New exploration licenses are not symbolic gestures. They represent a multi-decade commitment to extracting and eventually burning fossil fuels that, by definition, have not yet been discovered, let alone extracted, at a moment when the stated global goal is to reduce fossil fuel reliance as quickly as possible. Around the same period, geopolitical maneuvering around Venezuela, home to the largest known crude oil reserves on the planet, shifted control over how a significant portion of that oil reaches global markets, illustrating how strategic and economic interests around fossil fuel access continue to shape international relations even as climate rhetoric intensifies in parallel. None of this exists in a vacuum either. The head of the United Nations himself, speaking ahead of the most recent climate conference, acknowledged that overshooting the 1.5-degree target set out in Paris is now, in his own words, essentially inevitable, urging the world to recognize that particular failure honestly rather than continuing to pretend the original target remains realistically within reach. Independent climate research organizations have reached similar conclusions, describing the strict 1.5-degree ceiling as effectively unobtainable given the emissions trajectory the world remains on, and yet acknowledging that the strictest version of the Paris target is likely out of reach is a very different statement from concluding that nothing further can be done. And it is worth spending real time on why that distinction matters. Because it is the difference between despair and strategy. Even after the Paris Agreement set 1.5 degrees as an aspiration, climate scientists began quietly working through what achieving that number would actually require in practice. And the emerging consensus settled on something called a temporary overshoot scenario. The basic idea is that global temperature is likely to exceed 1.5 degrees for some period, possibly reaching somewhere in the range of 1.7 to 1.8 degrees at its peak around the middle of this century, before being pulled back down below that threshold by the year 2100 through a combination of steep emissions, cuts, and active carbon removal. In other words, the current scientific framing already assumes we will overshoot the original target and then have to claw our way back afterward, which is itself a quiet admission that the clean, linear path envisioned back in 2015 is no longer realistic. Pulling off that kind of recovery, even in principle, requires deploying essentially every mitigation tool simultaneously rather than picking a favorite and hoping it carries the weight alone. That means continued build out of renewable electricity generation, deep improvements in energy efficiency across buildings and industry, rapid electrification of transportation, large-scale reforestation and ecosystem restoration, methane leak reduction across the oil, gas, and agricultural sectors, and changes in consumption patterns at a societal scale. It also increasingly means embracing technologies that would have sounded like science fiction only 2 decades ago, including direct air capture facilities that physically pull carbon dioxide out of ambient air and store it underground, and the use of biochar, a stable, carbon-rich material produced by heating organic matter in the absence of oxygen, which can lock carbon into soil for centuries at a time, getting the planet back below 1.5 degrees after an overshoot effectively requires reaching net negative emissions later this century, meaning humanity would need to remove more carbon dioxide from the atmosphere each year than it releases, a state the world has never operated in throughout the entire industrial era. There is genuine reason for cautious optimism buried inside this otherwise bleak picture, and it comes from an unexpected direction: cost curves rather than willpower. Since around 2010, the cost of solar power, wind power, and lithium-ion batteries has fallen by roughly 85%. That is not a modest efficiency gain. It is one of the fastest cost declines ever recorded for an energy technology, faster than most forecasters predicted even a decade ago. Solar and wind power are now the cheapest source of new electricity generation across large parts of the world, in many cases cheaper than continuing to operate existing fossil fuel plants, let alone building new ones. This matters because it removes one of the oldest excuses in the climate debate: the idea that clean energy is simply too expensive to deploy at the scale required economically in a growing number of markets. That argument has already collapsed. Policy has, at least on paper, moved in step with that cost decline. By 2022, more than 170 countries had incorporated some combination of climate adaptation and mitigation measures into their national planning frameworks, a dramatic increase from where things stood only a decade or 2 earlier. The chair of the world's leading climate science body has stated plainly that humanity already possesses the tools and the technical knowledge required to limit warming to survivable levels. The tools existing and the tools being deployed at the necessary speed remain 2 very different things, and that gap, more than any single missing piece of technology, is the actual battlefield this fight is being decided on. There is also a set of risks operating beneath the surface of all these numbers that deserves mention, commonly referred to as climate tipping points. These are thresholds within the Earth's system where a relatively small additional nudge of warming could trigger a much larger, self-sustaining, and potentially irreversible shift. The circulation pattern that moves warm water through the Atlantic Ocean, sometimes described using the acronym AMOC, has shown signs of long-term weakening in multiple independent studies, and some researchers have raised the possibility, still debated, that it could undergo a more abrupt collapse under continued warming, with dramatic consequences for weather patterns across Europe and beyond. Permafrost across the Arctic, frozen ground that has locked away vast stores of ancient carbon and methane for thousands of years, is beginning to thaw in a growing number of regions, threatening to release greenhouse gases that were never accounted for in most standard emissions projections in the first place. The Amazon rainforest, meanwhile, faces a combination of warming, deforestation, and drought severe enough that some ecologists worry large sections could eventually shift from dense rainforest into a drier, savanna-like ecosystem, a transition that, once it truly gets underway, would be extraordinarily difficult to reverse on any human timescale. None of these tipping points are guaranteed to occur at any specific temperature, and the exact thresholds remain an active area of scientific research and legitimate scientific disagreement. But their mere existence is precisely why locking in unnecessary additional warming now is such a dangerous gamble. Since it raises the odds of crossing thresholds we do not fully understand and cannot easily undo. It is worth taking a short detour into how scientists actually arrived at this understanding in the first place, because the history is longer and more deliberate than most people realize, and it undercuts any suggestion that climate science is some recent, rushed, or politically motivated invention. As early as 1856, an American scientist named Eunice Foote ran laboratory experiments showing that carbon dioxide trapped heat more effectively than ordinary air, though her work went largely unrecognized for over a century. A few years later, physicist John Tyndall conducted more detailed measurements confirming that gases like carbon dioxide and water vapor absorb infrared radiation, effectively laying the experimental groundwork for the greenhouse effect. By 1896, a Swedish chemist named Svante Arrhenius had gone a step further, calculating, using nothing more than pen, paper, and painstaking arithmetic, roughly how much the planet's surface temperature would rise if atmospheric carbon dioxide concentrations doubled. His estimate, produced over a century ago with none of today's satellites, computers, or global monitoring networks, still sits within a reasonable range of modern climate model projections, which is a remarkable testament to how solid the underlying physics has always been. The modern era of direct measurement began in 1958, when a scientist named Charles David Keeling set up continuous carbon dioxide monitoring equipment atop the Mauna Loa volcano in Hawaii, chosen specifically because its high altitude and isolation from major population centers made it an unusually clean place to sample the global atmosphere. The resulting graph, now known simply as the Keeling Curve, has run continuously for well over 6 decades, and it shows an unmistakable, almost perfectly smooth upward climb overlaid with small seasonal wiggles caused by plant growth cycles in the northern hemisphere. It remains one of the most important and most visually simple pieces of evidence in all of environmental science. A single continuous line that has watched the atmosphere change in close to real time across the entire span of the modern climate debate. Sea level rise deserves its own attention here too, because unlike a heat wave or a hurricane, it rarely produces a single dramatic headline moment. It simply creeps upward year after year, reshaping coastlines by centimeters rather than announcing itself all at once. Global average sea level has already risen by somewhere in the range of 20 to 25 centimeters since 1800, driven by a combination of thermal expansion, as warmer ocean water physically takes up more volume, and the melting of land-based ice from glaciers and the ice sheets covering Greenland and Antarctica. The rate of that rise has itself been accelerating, roughly doubling over the past 3 decades compared to the earlier 20th century average, for low-lying island nations and coastal megacities alike. Even a further rise measured in tens of centimeters translates into more frequent flooding during storms, saltwater intrusion into freshwater aquifers and farmland, and in the most severe long-term projections, the eventual displacement of entire communities that have occupied the same coastlines for generations. Researchers at Stanford University have modeled the probability of exceeding the looser 2 degrees Celsius threshold under a range of future emissions pathways, and their analysis found that even in a scenario where humanity successfully reaches net zero emissions by the 2050s, a genuinely ambitious target by current standards, there remains roughly a 50% chance that global warming still breaches 2 degrees at some point regardless. That statistic captures something important about the momentum already built into the climate system, because carbon dioxide lingers in the atmosphere for centuries after it is released. and because the ocean takes decades to fully respond to changes in atmospheric composition. Today's warming reflects decisions made decades ago, and today's emissions will continue, influencing the climate long after any of us are alive to see the full consequences play out. At the planet's current average warming rate, estimated at roughly 0.27 degrees per decade, a pace faster than anything visible anywhere in the geological record, researchers estimate that as many as 3.6 billion people, nearly half of humanity, would end up living in conditions classified as highly vulnerable to climate-related stress. There is also a deep unfairness embedded in how these risks are distributed around the planet, and it is worth naming plainly rather than glossing over. The nations that have historically contributed the least to cumulative global emissions, largely across sub-Saharan Africa, South Asia, and small island states scattered through the Pacific and Caribbean, tend to face some of the most severe and immediate consequences. From crop failures and water scarcity to the direct, existential threat of rising seas swallowing low-lying territory entirely. Meanwhile, the wealthiest nations, responsible for the overwhelming majority of historical emissions, generally possess the financial and infrastructural resources to adapt, at least for now, insulating much of their population from the worst immediate effects. This imbalance sits at the center of ongoing, often contentious negotiations over climate finance, where wealthier nations have repeatedly pledged funding to help developing nations adapt to and mitigate climate impacts, only to fall consistently short of the amounts promised year after year. At conference after conference, food security sits downstream of almost every trend already discussed. Shifting rainfall patterns, more frequent and more intense droughts, and heat stress on staple crops like wheat, rice, and maize are already measurably reducing agricultural yields in multiple major growing regions, even as the global population and its food demands continue to grow. Some regions are seeing entire growing seasons shortened or disrupted, forcing farmers to adapt crop choices or, in the most severe cases, abandon land that has been cultivated for generations. Combined with disruptions to fisheries caused by ocean warming and acidification, this creates a genuine long-term threat to global food supply chains that operates quietly in the background of the more visible disasters that tend to dominate headlines. The economic side of this story has also shifted noticeably in recent years, most visibly through the insurance industry, which exists specifically to price risk accurately or go out of business trying. In a growing number of high-risk regions, particularly parts of the United States prone to wildfire and hurricane damage, major insurers have begun quietly withdrawing coverage altogether, or raising premiums to levels many homeowners can no longer afford, effectively pricing climate risk into everyday life, whether governments choose to acknowledge that risk directly or not. When an industry built entirely around calculating probability starts retreating from an entire category of risk, that is arguably one of the clearest, least politically charged signals available that something in the underlying system has genuinely changed. Migration patterns are beginning to shift in response as well, though this remains one of the more difficult effects to measure precisely, since people rarely migrate for a single isolated reason. Droughts, crop failures, and repeated flooding increasingly act as one contributing factor among several driving internal displacement and, in some cases, cross-border migration, particularly across parts of Central America, the Sahel region of Africa, and South Asia. Researchers studying this phenomenon are generally careful to describe climate change as a threat multiplier rather than a sole cause, since it tends to worsen existing pressures around resource scarcity, economic instability, and political conflict rather than acting entirely on its own. But as extreme events become more frequent, that multiplying effect becomes harder to separate from the underlying trend it is amplifying. It is easy, sitting through a video like this one, to conclude that every country and every energy system is failing in exactly the same way. But that flattens some genuinely interesting variation worth acknowledging. Denmark now generates a majority of its electricity from wind power alone, built up methodically over several decades of consistent policy support. Costa Rica has run its electrical grid on close to entirely renewable sources for extended stretches in recent years, relying heavily on hydroelectric, geothermal, and wind generation. Uruguay transformed its electricity mix from heavily fossil fuel dependent to overwhelmingly renewable in less than 15 years, driven largely by wind investment. China, despite remaining the single largest annual emitter of greenhouse gases in the world today, also installs more new solar and wind capacity each year than the rest of the world combined, illustrating just how tangled the picture becomes once you look past a single headline statistic. Since the same country can simultaneously be the largest source of new emissions and the largest source of new clean energy capacity in any given year. Electric vehicle adoption offers another useful case study in how quickly a technology can move. Once cost and infrastructure reach a certain tipping point of their own, little more than a decade ago, electric vehicles represented a tiny, expensive niche within the broader auto market. Today, in several major markets, including large parts of Europe and China, electric vehicles account for a substantial and rapidly growing share of new car sales, driven by falling battery costs, mirroring the same steep decline seen in solar and wind. Alongside expanding charging infrastructure and increasingly competitive vehicle range, transportation remains one of the largest single sources of emissions in many wealthy economies, which makes this shift, however incomplete, one of the more consequential trends currently underway. Grid-scale battery storage represents a quieter but equally important piece of the puzzle, because one of the oldest criticisms of solar and wind power was always their intermittency. The simple fact that the sun does not always shine and the wind does not always blow exactly when electricity demand peaks. Advances in battery technology, alongside falling costs mirroring the broader renewable energy trend, have begun meaningfully closing that gap, allowing grids to store excess renewable generation during low demand periods and release it during high demand periods instead. Some regions have moved further still, exploring longer duration storage technologies and smarter, more flexible grid management systems designed specifically to handle a future where the majority of electricity comes from variable, renewable sources rather than steady, always-on fossil fuel plants. Nuclear power occupies a more contested position in this conversation, generating a reliable, low-carbon source of electricity that does not depend on weather conditions, but carrying its own set of challenges around construction cost, build time, waste management, and public perception shaped heavily by a small number of historical accidents. Several countries have recently reversed earlier decisions to phase out nuclear power, extending the operating life of existing plants or exploring new reactor designs, partly in response to the recognition that reliable, always available, low-carbon electricity remains genuinely difficult to source from. Renewables alone, without extensive storage infrastructure, still being built out. Public pressure has also visibly shifted over the past decade in ways that are easy to underestimate simply because change of this kind tends to be gradual rather than sudden. Youth-led climate movements, largely organized and amplified through social media, have grown from small, localized protests into coordinated global actions involving millions of participants across dozens of countries. Climate litigation, once a rare and largely symbolic legal strategy, has expanded into a genuine and growing body of case law, with courts in multiple countries ruling in favor of plaintiffs, arguing that governments have a binding legal obligation to protect current and future generations from the consequences of climate inaction. None of this guarantees policy outcomes on its own, but it represents exactly the kind of sustained cultural and political pressure that, over long enough timescales, has historically preceded major shifts in how governments and industries operate. It is also worth acknowledging, briefly and honestly, that living through this information can itself take a psychological toll. Surveys conducted across multiple countries in recent years have found a significant share of young people, reporting, genuine anxiety about the future of the planet they are inheriting, a phenomenon researchers have started referring to as climate anxiety or eco-anxiety. This is not a fringe reaction. It is an increasingly well-documented and studied response to a genuinely difficult set of facts. And mental health professionals in a growing number of countries have begun incorporating it directly into how they think about supporting young patients specifically. So, where does all of this actually leave the original claim that started this conversation? The idea that humanity has lost the fight against climate change entirely. The scientific bodies actually responsible for tracking this problem have been notably careful not to frame the situation in such absolute terms. And it is worth understanding why. Because it is not naivety, it is a specific, deliberate distinction between two very different questions. The first question is whether the strict, original 1.5-degree target set out in Paris remains realistically achievable without any overshoot at all. On the evidence laid out across this video, the honest answer to that specific question is almost certainly no. The second, separate question is whether meaningful, consequential action to limit total warming and reduce long-term suffering remains possible. On that broader question, the leading scientific consensus continues to answer yes. And the difference between those two answers is not a technicality. It is the entire difference between resignation and strategy. Every fraction of a degree of warming avoided translates directly into fewer extreme heat deaths, fewer catastrophic storms, fewer square kilometers of coral reef lost, fewer climate-driven conflicts over shrinking resources, and fewer people forced to abandon land their families may have lived on for generations. There is no meaningful threshold beyond which further mitigation stops mattering. No cliff edge past which effort becomes pointless. A world that stabilizes at 2.2 degrees of warming is measurably, substantially better than one that stabilizes at 3.5 degrees. Even though both numbers would have sounded catastrophic to anyone reading the very first climate reports back in the 1980s. This is precisely why climate scientists keep pushing for stronger action, even after acknowledging that the original, cleanest version of the target has likely slipped away. Every additional fraction of a degree avoided is not a rounding error. It is measured in millions of human lives and entire ecosystems that either persist or disappear. None of this erases the genuine anger that a statement like David Suzuki's is likely to provoke. And it probably shouldn't. The historical record laid out across this video, decades of scientific warning paired with decades of comparatively modest action, is a legitimate source of frustration, and it would be strange for anyone paying close attention to feel calm about it. But there is a meaningful difference between channeling that anger toward disengagement and channeling it toward continued pressure, continued attention, and continued demand for the kind of large-scale, structural change that individual choices alone were never going to deliver on their own. The data throughout this video is not an argument for giving up. It is an argument for understanding precisely how much is genuinely at stake in whatever time and capacity for action remains. If any part of what you have just heard resonated with you, sharing this kind of information further and staying subscribed to whichever source keeps you informed on how this story develops does something small but genuinely real. It keeps this conversation visible at a moment when visibility itself is one of the most valuable political resources available. This is not a request built around vanity metrics. It is simply an acknowledgement that public attention has historically been one of the more reliable precursors to public pressure, and public pressure has historically been one of the more reliable precursors to policy change. However slow and frustrating that particular chain of cause and effect can feel while you are living through it, it is also worth being honest about what remains genuinely uncertain in all of this. Because a fact-driven account of climate change should not pretend the science is settled down to every last decimal point. Even while the core physics remains beyond serious dispute, climate models, however sophisticated they have become, still carry meaningful uncertainty around a handful of specific processes. Cloud behavior under warming conditions remains one of the more stubborn open questions, since clouds can either trap additional heat or reflect additional sunlight away depending on their altitude, thickness, and location. And small changes in how clouds respond to warming can meaningfully shift the overall sensitivity of the climate system in either direction. Researchers refer to this as cloud feedback, and narrowing the uncertainty around it remains an active area of ongoing atmospheric research. Using both satellite observation and increasingly detailed computer simulation, ice sheet dynamics, particularly across West Antarctica, represent another significant zone of scientific uncertainty, not because scientists doubt the ice is melting, but because the exact speed at which certain glaciers could destabilize remains difficult to pin down precisely. Some glaciers sit on bedrock that slopes downward toward the interior of the continent, a geometry that can, under the wrong conditions, allow melting to accelerate in a self-reinforcing feedback loop once it begins in earnest, a process researchers sometimes call marine ice sheet instability. Whether and how quickly that kind of instability could unfold in specific glaciers remains one of the most actively studied and most consequential open questions in all of climate science, because it directly affects how quickly sea levels could rise in the coming decades. Under different warming scenarios, methane, released from thawing permafrost and disturbed wetlands, adds another layer of complexity. Because methane traps significantly more heat than carbon dioxide over short timescales, even though it breaks down in the atmosphere much faster. Current emissions projections generally account for anthropogenic methane sources with reasonable confidence. Industrial leaks, livestock, rice cultivation, and so on. But the potential for large-scale natural methane release from a warming Arctic remains harder to quantify precisely, and represents exactly the kind of feedback loop that could, in principle, push warming beyond what current models predict if it accelerates faster than anticipated. There is also ongoing uncertainty around what scientists call aerosol masking, which sounds technical but describes something fairly intuitive. Certain forms of air pollution, particularly sulfate aerosols, released alongside fossil fuel burning, actually reflect sunlight and have a cooling effect on the atmosphere, partially offsetting some of the warming caused by greenhouse gases from the very same sources. As countries clean up air pollution for public health reasons, which is unambiguously good news for human health, they may simultaneously remove some of this incidental cooling effect, potentially revealing more of the underlying warming that greenhouse gases alone would otherwise produce. Untangling exactly how much cooling this masking effect currently provides, and how quickly it might diminish as pollution controls tighten globally, remains an active and genuinely important area of climate research. On the technology side, research into large-scale carbon removal is advancing rapidly but remains, for now, a small fraction of what would ultimately be required under the overshoot scenarios described earlier in this video. Direct air capture facilities currently operating around the world remove a comparatively tiny amount of carbon dioxide each year compared to global emissions, measured in the thousands or low millions of tons, rather than the billions of tons that net negative emission scenarios eventually require. Scaling this technology up by several orders of magnitude, while keeping its energy and financial costs manageable, represents one of the largest engineering challenges of the coming decades, and researchers across multiple countries continue working on both the underlying chemistry and the economics required to make it viable at a truly global scale. More controversial research continues into what is sometimes called solar radiation management, a category of proposed interventions that would attempt to directly reflect a small amount of sunlight away from Earth, for example, by releasing reflective particles into the upper atmosphere, deliberately mimicking the temporary cooling effect of a large volcanic eruption. Unlike carbon removal, which addresses the root cause of warming, this kind of intervention would only mask the temperature symptom while doing nothing about the underlying greenhouse gas concentration, and it carries its own set of poorly understood risks around regional weather disruption, ecological side effects, and the thorny governance question of who, exactly, gets to make a unilateral decision that would affect the entire planet's climate at once. Some limited outdoor experiments have already drawn significant public controversy and, in at least one case, direct opposition from local communities and regulators, illustrating just how contested this particular avenue of research remains even among scientists who otherwise broadly agree on the urgency of the underlying problem. The next major, comprehensive assessment from the world's leading climate science body is expected later this decade, incorporating an additional several years of updated observational data, improved modeling techniques, and a more refined understanding of the specific feedback loops described above. Each successive assessment has, so far, tended to sharpen rather than soften the underlying picture, narrowing uncertainty ranges around key figures like the carbon budget and the climate's overall sensitivity to added greenhouse gases, generally in the direction of confirming that the situation is at least as serious as previously understood, and in some specific areas, somewhat more urgent than earlier assessments suggested. Some of the clearest, most visually striking evidence of a changing climate comes from the polar regions, which warm considerably faster than the global average, a phenomenon researchers call Arctic amplification. This happens largely because of a feedback loop involving ice and reflectivity. Fresh snow and sea ice reflect a large portion of incoming sunlight back to space, but as that ice melts, it exposes darker ocean water and land underneath, which absorbs far more solar energy than the ice it replaced, accelerating further warming and further melting in a self-reinforcing cycle. As a result, the Arctic has warmed at roughly 2 to 4 times the global average rate over recent decades, a disparity visible in satellite imagery showing summer sea ice extent shrinking dramatically compared to just a few decades ago. Some climate models now project that the Arctic Ocean could experience its first largely ice-free summer sometime within the next few decades, an event that would have been considered essentially unthinkable across the entire span of recorded human history. Glaciers outside the polar regions tell a similarly stark story. Mountain glaciers across the Alps, the Andes, the Himalayas, and elsewhere have retreated dramatically over the past century, with the rate of ice loss accelerating noticeably in recent decades. This matters well beyond the loss of scenic mountain landscapes, because hundreds of millions of people downstream of major glacier systems, particularly across parts of South Asia fed by Himalayan melt, depend on glacial melt for a meaningful share of their fresh water supply, especially during dry seasons when rainfall alone is insufficient. As these glaciers shrink, researchers project an initial temporary increase in meltwater volume, followed eventually by a longer-term decline once the glaciers themselves have lost too much mass to sustain current flow rates, creating a looming water security challenge for some of the most densely populated regions on the planet. Marine ecosystems face their own version of this compounding pressure, extending well beyond the ocean, acidification, and coral reef stress already discussed. Marine heat waves, periods of unusually high ocean temperatures that can persist for weeks or months at a time, have become measurably more frequent and more intense in recent decades. One such event in the northeastern Pacific Ocean around the middle of the past decade, sometimes referred to informally by researchers using the nickname the blob, persisted for an extended period and triggered widespread disruptions across the marine food web, from mass die-offs of seabirds struggling to find prey, to closures of commercially important fisheries, to unusual whale migration patterns as the animals followed shifting prey populations into new territory. Coral bleaching events, triggered when unusually warm water causes corals to expel the symbiotic algae that give them both their color and much of their energy supply, have shifted from rare, isolated occurrences to a recurring, near-annual concern across major reef systems, including Australia's Great Barrier Reef, which has experienced multiple severe, widespread bleaching events within just the past decade alone. Biodiversity loss, more broadly, compounds all of these pressures simultaneously. Species across virtually every ecosystem on the planet are being forced to adapt to shifting temperature and precipitation patterns faster than many of them are capable of adapting through natural evolutionary processes, which generally require many generations to meaningfully reshape a species' tolerance for a changing environment. Some species are shifting their geographic range toward the poles or to higher elevations in search of historically familiar temperature conditions, a measurable trend documented across birds, insects, and plants alike. Others, particularly species with narrow habitat requirements, nowhere left to migrate to, or slow reproductive cycles that cannot keep pace with the speed of change, face meaningfully elevated extinction risk, combined with more direct pressures like habitat destruction and pollution, which fall under the land system change and novel entities planetary boundaries discussed earlier. Climate change increasingly functions as a compounding, rather than isolated, threat to global biodiversity. Human health faces knock-on effects well beyond the direct heat-related mortality already discussed. Warmer temperatures and shifting rainfall patterns are expanding the geographic range in which disease-carrying mosquitoes can survive and reproduce, raising the risk of diseases like malaria and dengue fever spreading into regions that have historically remained largely free of them, including higher elevation areas that were previously too cool for these mosquito populations to establish themselves. Air quality interacts with rising temperatures in another compounding way, since hotter conditions accelerate the chemical reactions that produce ground-level ozone pollution, a respiratory irritant linked to worsened asthma and other chronic respiratory conditions, layering additional health burden on top of the direct effects of heat itself. Urban areas face a further localized amplification of all of this, through what researchers call the urban heat island effect, where dense concentrations of concrete, asphalt, and buildings absorb and retain heat far more effectively than natural landscapes, making cities measurably hotter than surrounding rural areas, particularly overnight when that stored heat radiates back out and prevents temperatures from cooling down the way they would in a less developed area. Adaptation, as distinct from mitigation, has also become an increasingly serious engineering and policy discipline in its own right. precisely because a certain amount of further warming and disruption is now considered locked in, regardless of how aggressively emissions are cut going forward. The Netherlands, a country where a significant portion of the population lives below sea level, behind an extensive network of dikes, pumps, and storm barriers, has spent decades refining flood defense engineering that other coastal nations increasingly study and adapt for their own use. Some of the barrier systems protecting major Dutch cities are specifically designed and regularly upgraded to withstand storm surge conditions expected to become more frequent as sea levels continue rising, representing one of the more sophisticated examples of proactive, rather than purely reactive, climate adaptation currently in operation anywhere in the world. Managed retreat, the deliberate, planned relocation of communities away from areas that have become too vulnerable to flooding, erosion, or repeated disaster to remain safely inhabited, has moved from a theoretical policy concept into an active, if still relatively rare, practice in a number of countries. Certain coastal communities in the United States, several small Pacific island nations facing existential sea level threats, and some low-lying river delta regions in South and Southeast Asia have already begun formal relocation processes, or are actively planning for them, acknowledging that in certain specific locations, defending existing infrastructure indefinitely is no longer considered a realistic long-term strategy compared with an orderly, planned relocation instead. Agricultural adaptation research has similarly accelerated, with plant breeding programs working to develop crop varieties more tolerant of drought, heat, and soil salinity, the last of which becomes an increasing concern in coastal farming regions as rising seas push saltwater further into groundwater and irrigation systems. Some of this research builds on genetic diversity preserved in seed banks established decades ago, specifically as an insurance policy against exactly this kind of future agricultural stress, illustrating a rare case where forward-thinking conservation work undertaken generations ago is now proving directly useful in addressing a threat that, at the time those seed banks were established, had not yet become the dominant framing for why crop diversity mattered. Early warning systems represent another area where relatively modest investment appears to deliver outsized benefit. Improved forecasting technology, satellite monitoring, and community-level warning infrastructure have measurably reduced death tolls from certain categories of extreme weather event over recent decades, even as the underlying frequency and intensity of those events has increased. Cyclone warning systems developed and refined across South Asia, for instance, are widely credited with dramatically reducing storm-related fatalities compared to similarly powerful storms that struck the same regions decades earlier, before comparable warning infrastructure existed, demonstrating that even without solving the root cause of a more volatile climate, targeted investment in preparedness and response infrastructure can still meaningfully reduce the human cost of the disasters that do occur. The economics of all this eventually reduced to a fairly simple, if uncomfortable, comparison, one that economists have been modeling in various forms for close to 2 decades now. Every dollar spent today on mitigation, adaptation, and resilient infrastructure needs to be weighed against the dollar cost of the damage that inaction would otherwise produce further down the line, spread across insurance payouts, disaster recovery, lost agricultural productivity, and disrupted supply chains. Nearly every major economic analysis conducted on this question, regardless of which specific assumptions or discount rates the researchers apply, has reached broadly the same conclusion: that the long-term economic cost of unmitigated climate change substantially exceeds the upfront cost of aggressive, near-term action, sometimes by a wide margin. This is not, in other words, purely an environmental argument being made at the expense of economic interests. It increasingly functions as an economic argument in its own right, one that happens to align with the environmental case rather than conflicting with it. It is worth pausing on one particular psychological trap that this entire body of evidence can lead people toward, because it is subtle and, in its own way, just as counterproductive as outright denial ever was. Researchers who study public engagement with climate change have identified what is sometimes called climate doomism, a state in which someone fully accepts the seriousness of the science, but concludes from that acceptance that meaningful action is now pointless, that collapse is inevitable, and that continued effort amounts to nothing more than a delay tactic against an unavoidable outcome. On the surface, doomism can look like a hard-nosed, realistic response to genuinely alarming data, but functionally, it produces the exact same outcome as denial does. Reduced pressure on the institutions actually capable of driving large-scale change, simply arrived through a different psychological route. Understanding the difference between clear-eyed realism about how serious the situation is, and a fatalistic conclusion that nothing further is worth attempting, turns out to matter enormously for how this entire story ultimately plays out. History offers a handful of genuine precedents for what rapid, large-scale mobilization in response to an existential threat can actually look like, even if none of them map perfectly onto the climate challenge. During the Second World War, entire national economies, most notably that of the United States, reorganized their industrial base within a matter of a few short years, converting car factories into aircraft and tank production lines at a pace that, viewed from before the war began, would have seemed logistically impossible. That comparison is imperfect in obvious ways. A declared military conflict with a clearly identified enemy generates a different kind of political unity than a slow-moving, diffuse, globally distributed environmental threat with no single visible adversary. But it remains a useful reminder that the physical and industrial capacity for extremely rapid, coordinated transformation does exist within modern economies when the political will to deploy it is present. And the ozone layer recovery, already discussed in this video, stands as a smaller but far more directly comparable proof that the same logic can apply specifically to an atmospheric environmental threat. Not just to wartime industrial output, corporate accountability continues evolving as well, extending beyond the litigation trends mentioned earlier. A growing number of jurisdictions have begun requiring companies above a certain size to disclose their climate-related financial risks and greenhouse gas emissions in a standardized, auditable format, treating climate exposure as a material financial risk deserving the same rigor applied to any other line item on a balance sheet, rather than as an optional footnote in a corporate sustainability report. Shareholder activism has intensified in parallel, with a growing number of institutional investors, including some of the largest pension funds and asset managers in the world, publicly pressuring fossil fuel companies to disclose transition plans, reduce emissions intensity, or in some cases, divesting from fossil fuel holdings altogether as part of broader portfolio risk management strategies rather than purely as an ethical statement. Generational framing has also shifted noticeably over the past decade, moving from an abstract, distant concern about future generations toward a much more immediate, personal reckoning among people who are already adults today and will live through the bulk of these consequences firsthand, rather than merely worrying about consequences their grandchildren might eventually face. Surveys tracking public opinion across multiple countries have found steadily rising concern about climate change among younger age groups specifically, alongside growing frustration directed at older generations and existing political institutions. perceived as having had ample time, resources, and scientific warning to act decisively, and having largely failed to do so at the scale the moment required, something worth clarifying directly, because it gets lost easily in a conversation full of large numbers and dire statistics, is what winning this fight would even look like at this stage, since the original, cleanest definition of victory, holding warming under 1.5 degrees with no overshoot whatsoever, is very likely no longer available to us. A more honest, updated definition of success looks less like a single finish line and more like a continuous effort to minimize total accumulated harm across every fraction of a degree still within reach. Under that more realistic framing, the difference between a world that stabilizes warming near 2 degrees through aggressive, sustained action, and a world that drifts passively toward 3.5 or 4 degrees through continued inaction, represents an enormous, measurable difference in outcomes. Even though neither scenario matches the original ambition set out in Paris a decade ago, billions of people, the survival of entire ecosystems like warm water, coral reefs, and the stability of vast regions of low-lying coastline all sit within that remaining range of possible outcomes, which is precisely why treating this as a binary between total victory and total defeat badly misrepresents what is actually still at stake. The remainder of this decade has been described by a number of climate scientists and international organizations as a uniquely decisive window, not because some hard, physical deadline expires the moment the calendar turns, but because the cumulative total of emissions released between now and 2030 will meaningfully determine how much additional warming is already locked into the system for decades afterward, given how long carbon dioxide persists once it enters the atmosphere. Choices made or avoided within roughly the next 5 years carry disproportionate weight compared with choices made later, simply because there is more remaining carbon budget available to influence rights now than there will be once a larger share of it has already been spent. Children born within the past few years will reach their 40th birthday somewhere around the middle of this century, right around the point when many of the temperature trajectories discussed throughout this video are projected to reach their peak severity under an overshoot scenario, and their 80th birthday will fall close to the year 2100. The Horizon most long-range climate projections use as their reference point for where warming might eventually stabilize, assuming humanity manages to bring emissions back down toward net negative levels in the intervening decades. In other words, the entire span of currently projected climate outcomes, the peak of an overshoot and the hoped-for recovery afterward, is likely to unfold within a single ordinary human lifetime that has already begun. This is not a distant, hypothetical future being discussed in the abstract. It is the lived, decades-long experience awaiting people who are, in many cases, already alive today at the most recent round of international negotiations. One of the more concrete outcomes involved further development of what is called a loss and damage fund, a financial mechanism specifically intended to help vulnerable nations cope with climate impacts they are already experiencing, as distinct from funding aimed purely at future mitigation or adaptation. The concept emerged from a fairly simple, hard-to-argue-with premise that nations bearing the least historical responsibility for cumulative emissions are often absorbing some of the most severe present-day damage, and that some form of direct financial support is owed as a matter of basic fairness rather than charity. In practice, actual contributions pledged toward this fund have repeatedly fallen well short of the sums researchers estimate would be needed to meaningfully cover the damage already occurring each year, a familiar pattern echoing the broader gap between diplomatic ambition and delivered funding that has characterized climate finance more broadly for well over a decade. Now, given how central specific numbers and claims are to this entire topic, it is worth spending a moment on how to evaluate a striking statement like the one that opened this video, because the same evaluation process applies to virtually any bold claim about climate change encountered anywhere online. The most useful first question to ask is whether a claim traces back to a peer-reviewed study, an established scientific body, or a named, credentialed researcher speaking within their specific area of expertise, as opposed to a viral social media post stripped of any original source. The second useful question is whether the claim distinguishes between an already observed trend, backed by direct measurement, and a projection about the future, which necessarily carries a wider range of uncertainty attached to it. The third is whether a specific number is being presented with any acknowledgement of the error, bars or confidence intervals surrounding it, since real climate science, almost without exception, comes wrapped in some explicit range of uncertainty, and a claim that omits any hint of that uncertainty is often, though not always, oversimplified for effect. None of this means bold, alarming claims are automatically wrong. Several of the ones already covered in this video are both genuinely alarming and well supported by the underlying data. But developing the habit of tracing a striking statement back to its actual source is one of the more useful, transferable skills available for navigating an information environment that increasingly rewards the most dramatic possible framing of any given fact. So, to bring this back to where it started, has humanity lost the fight against climate change? If the fight is defined narrowly as holding warming under 1.5 degrees with no overshoot whatsoever, then yes, on the evidence laid out across this entire video, that specific, narrow fight is almost certainly over, and it was lost through a recognizable, well-documented sequence of missed deadlines, diluted commitments, and continued fossil fuel expansion stretching back over 3 decades. But if the fight is understood more broadly, as the ongoing effort to limit total accumulated warming, protect as much of the natural world and as many vulnerable communities as remains possible, and eventually pull the climate system back down from whatever peak it reaches later this century, then the fight has not ended at all. It has simply entered a harder, less forgiving phase than the one negotiators originally signed up for a decade ago in Paris. What remains genuinely unknown is not whether the underlying physics is real. That question was settled by repeated, independent lines of evidence stretching back well over a century. From laboratory experiments to ice cores to direct atmospheric measurement, what remains unknown is the precise timing and severity of specific tipping points, the exact pace at which clean energy, technology, and carbon removal can be scaled globally, the specific policy and political developments still to come across dozens of national governments, and ultimately, the collective choices billions of individual people and thousands of institutions have not yet made. Ongoing research into cloud feedback, ice sheet dynamics, permafrost, methane release, and large-scale carbon removal will continue narrowing some of that uncertainty in the years ahead, even as the underlying trend line, more carbon in the atmosphere, higher average temperatures, more frequent extreme events, continues in the direction it has followed for decades. That combination, settled fundamentals, paired with a still open, still contested future, is exactly why this remains one of the most scientifically active and consequential subjects of the current era. Not despite the discouraging data covered throughout this video, but because of it. The physics closed the door on easy answers a long time ago. What happens next, across a decisive decade already underway, remains, for better or worse, still being written. One mechanism worth understanding in a bit more depth, because it comes up constantly in serious policy discussions without always being explained clearly. Is carbon pricing the general strategy of attaching a direct financial cost to releasing greenhouse gases, on the theory that markets respond more efficiently to a clear price signal than to a patchwork of individual regulations alone? This generally takes one of two forms. A carbon tax sets a fixed price per ton of emissions released, giving businesses a predictable cost to plan around, while a cap-and-trade system instead sets a hard limit on total allowable emissions across an economy or sector, then lets companies buy and sell a limited number of permits within that cap, allowing the market itself to determine the resulting price. The European Union operates one of the largest and longest-running cap-and-trade systems in the world, covering power generation and heavy industry across dozens of countries. And the price per ton of carbon within that system has, at various points, climbed high enough to noticeably shift investment away from coal-fired power generation and toward cleaner alternatives, offering a real-world case study in how a well-designed price signal can measurably influence corporate investment decisions over time, even without a single new regulation being written for any specific industry. National policy has moved in fits and starts across major economies as well. The European Union's broader climate policy framework, often referred to collectively as the Green Deal, set binding targets for emissions reduction and renewable energy deployment across all member states. Backed by significant public investment funding, the United States passed a major piece of legislation in the early 2020s directing hundreds of billions of dollars toward clean energy manufacturing, electric vehicle incentives, and renewable power generation, representing one of the largest single climate-related public investments in that country's history, even as broader federal climate policy has continued to shift noticeably with each change in presidential administration, illustrating one of the more structurally difficult aspects of climate policy in any democracy: the risk that a multi-decade problem requiring sustained, consistent commitment gets subjected to policy reversals every few years as political power changes hands. China, structured very differently as a one-party state with long-range 5-year economic plans, has set its own binding targets for emissions intensity reduction and renewable capacity expansion, benefiting from a policy continuity that democratic systems generally struggle to replicate, even as the country continues to build significant new coal-fired power capacity in parallel with its renewable expansion, again illustrating the tangled, simultaneously encouraging and discouraging reality that characterizes nearly every major emitter's actual policy record. Once you look past the top-line announcements, none of these mechanisms or policies, on their own, resolve the underlying gap between what the science says is required and what has actually been delivered so far, but collectively, they represent the accumulated, if uneven and still insufficient, institutional response to 4 decades of accumulating scientific warning, and they form the actual toolkit available for closing that gap further in the years directly ahead, assuming the political will to expand and strengthen them continues to build rather than stall out entirely. Taken together, everything covered in this video, the missed targets, the record emissions, the crossed planetary boundaries, the accelerating extreme weather, alongside the falling clean energy costs, the expanding legal accountability, and the genuinely open scientific questions still being actively researched, adds up to a picture that resists a single, tidy headline. It is neither the reassuring story some would prefer to hear, nor the flatly hopeless one that a single dramatic quote might suggest on its own. It is something messier and, in its own way, more demanding of attention than either extreme. A problem largely understood, partially addressed, and still very much unresolved, unfolding in real time. with the next chapter shaped directly by decisions still being made across boardrooms, parliaments, laboratories, and, in whatever small way, everyday choices made by people who happen to be paying attention. It is also worth remembering that public understanding of this issue has itself evolved considerably over the past few decades, in ways that shape how effectively society can even respond in the first place. Opinion surveys conducted since the 1980s show a long, gradual climb in the share of people who accept the basic scientific consensus that human activity is the primary driver of recent warming, even as that acceptance has, at various points, become entangled with broader political identity in ways that make consensus building considerably harder than the underlying science alone would suggest it should be. Communication researchers have spent considerable effort studying why a topic with such overwhelming scientific agreement, routinely cited as exceeding 97% among actively publishing climate scientists, can still generate such persistent public disagreement. And much of that research points toward the way information is filtered through existing social and political identities long before it reaches any individual's personal assessment of the raw data itself. Media coverage patterns have shifted as well, moving gradually away from a once common practice of presenting climate change as a matter of ongoing scientific debate between two roughly balanced sides, toward coverage that more accurately reflects the genuinely lopsided nature of the actual scientific consensus, even if that shift has been slower and less complete than many climate communicators would prefer. Extreme weather events increasingly receive direct attribution analysis within days of occurring, thanks to a relatively young but rapidly maturing scientific discipline sometimes called extreme event attribution, which uses climate models to estimate how much more likely or how much more severe a specific heat wave, flood, or storm was made by the existing level of human-caused warming, compared to a hypothetical world without it. This is precisely the methodology referenced earlier regarding Hurricane Melissa, and it represents one of the more significant recent advances in translating abstract, long-term climate trends into concrete, near real-time statements about specific, individual weather disasters as they unfold. Looking specifically at what comes next on the research calendar, several major international assessments and negotiations are already scheduled for the remainder of this decade, each expected to incorporate updated emissions data, refined temperature projections, and further attribution studies connecting specific disasters back to the broader warming trend. Scientific monitoring networks, including the long-running Mauna Loa Observatory and its equivalents at other sites around the world, will continue producing the kind of continuous, unbroken measurement record that has underpinned this entire body of knowledge since the late 1950s, ensuring that whatever conclusions future researchers draw will rest on the same foundation of direct, verifiable observation that has defined climate science from its earliest instrumental beginnings through to the present day. Whatever specific numbers future assessments ultimately report, the broader trajectory described throughout this video, rising concentrations, rising temperatures, crossed planetary thresholds, and a narrowing but not entirely closed window for meaningful action, will remain the essential backdrop against which every future policy decision, technological breakthrough, and international negotiation gets measured. That is not a comfortable place to end a conversation like this one, but it is, as closely as the available evidence allows, an honest one. And an honest accounting of where things actually stand has always been the necessary first step toward changing where they end up going next. Whether that reckoning arrives through sweeping new policy, through the continued compounding progress of falling clean energy costs, or through the sheer undeniable accumulation of extreme weather events forcing action that diplomacy alone could not deliver, remains genuinely open. What is no longer open to serious scientific debate is the direction the underlying system is currently moving in, and the widening gap between the scale of that movement and the scale of the response it still requires. That gap, more than any single number covered in this video, is the real story still unfolding, one decade, one measurement, and one decision at a time.